Welcome to this lecture on transient heat transmission, the second part where we talk about transient conditions for rooms, where before we have talked about conditions for walls. Now we're talking actually about conditions for rooms that are adjacent to the walls, because the walls give some thermal capacity also to the rooms and possibly other objects also in the rooms than only the walls. The method that is part of this lecture here, that we're going to talk about here in these few slides, is invented by the former Swedish professor Bo Adamsson, so we call it Bo Adamsson's method. Now, what we'll talk about is the heat balance for a room that we have here on the picture. And initially, we set up some things where the room is in thermal balance with heat supply, heat gains in the room, and also heat losses to the outside of the room. So this balance is expressed down here, that we have initially a temperature within the room at time 0, so that's initial, and we have another temperature in principle outside of the room, and the difference between those two temperatures multiplied with a room coupling conductance, a coefficient that couples heat transfer between the room and the outside. Well, initially, since we have a balance, it means that we have to have all heat gains from radiators, from solar gains, people, what you have. Initially, such heat gain should be in balance with the heat losses. That's what it expresses here. The room coupling conductance, we can see, comes from heat transmission through the walls, where we multiply the area and the U values for all walls and sum them up. And also, we have heat transmission because of the ventilation heat loss, which we calculate the contribution for ventilation to the room coupling conductance by the last term here, air change, volume, density, and heat capacity of the air. That's all that, what we have. Now, we want to calculate things in a transient manner, so we should consider something with the room heat capacity. And for that, we take a part of the material that surrounds or that can be found in the room to contribute with heat capacity to that room. And then we consider a certain thickness of material, perhaps only. And that thickness we can very often, from the previous lecture, we can take as the penetration depth for that daily cycle. If you're studying daily variations, which is normal in buildings, what is the penetration depth of material that we should consider? We call that thickness delta. So that's the setting up of the model. Now, that was initially in equilibrium, but the idea of making it transient is to see what happens if suddenly we have a change in the condition. So at time 0, suddenly the heat gain that we had in the room is increased by a certain level, delta phi. So that means that if I write the equation from before, I should now write it a little bit differently. So because now we have the difference in the indoor temperature as it varies with time, again, compared to the outdoor temperature, the same coefficient that couples to the outdoor environment we still have, the initial heat gain that we had, and then the increase. That gives reason to a per time temperature increase where we need to consider the room heat capacity C. Now, if I just take the equation from the previous slide, then we can see how we can eliminate the initial heat gain in the room. And when we do that, then we have another equation where the outdoor temperature is replaced with initial temperature. So this tells us essentially, with that increase in heat gain, how is the development or the increase in temperature per time. The heat capacity of the room, we have to take for all those layers that surrounds the room, possibly materials within the room, furniture, what you have. So sum up all the contributions to the heat capacity from all such components in the room. Now, with the initial condition, as we talked about at time 0, well then we have the partial differential equation we can solve, and here comes the solution. It's an exponential decline towards a final solution for the time. So here is where we insert the time. You have as a coefficient in front of the time, you have the coupling coefficient, and you have the heat capacity. So that's our coefficient in this equation. 1 over that coefficient, that we call the time constant, which explains how slow it is. A long time constant, it takes a long time to change things. That goes with large heat capacity or a small coupling coefficient in our equation. So if we plot the temperature development here's the heat gain that we have, the heat load. We had an initial state, and suddenly we have an increase in the heat gain. Well then, at that moment, the temperature begins to increase, and here is the exponential decline towards the final solution. And the time constant, we can also kind of see visualized here. That's the time from the beginning until 63% of the change in temperatures that will occur if we wait long enough. 63% of that change has happened after one time constant. Then you can have another time constant, another and another, and gradually come closer to the final solution. But that is all explained by the equation we saw from before. So I'll just have a few words to say on that heat accumulating layer, so how much material we can consider in our calculation. And because there are a few rules of thumb of how much material really interacts with the air that we have in the room. So if you have a multi-layered structure, then we should consider only the layers that come before, possibly also an insulation layer. Also, normally, if we have heavyweight normal building materials, we don't see thicknesses larger than, say, around 10, 12 centimeters. Also depending on how well conducting the materials are. So for some lighter materials, we'll probably see slightly less, 5, 6 centimeters. If you have things that are symmetric, so you have a similar room on two sides of an interior wall, then you should of course consider only until the middle of the wall. Also, if the heat transmission into those layers in the wall is not so good, then we should consider only until we have a heat transmission coefficient into the layer, which has to be larger than 2 watts per square meter Kelvin. And also, considering the time constant, since we have different components contributing to giving heat capacity to the room, they should more or less be of similar time constant, each of the individual components. So for each wall or material, you can calculate its contribution to the time constant. And it should be not more than a factor, say 3, less or more than the average or the whole time constant for the whole room. And finally, 2 more things here. The first one here, that time constant for the layer that we consider should not exceed 1 daily variation if we're talking, as I said before, normally about daily variations. And when we calculate that, it corresponds to having a time constant with the definition I introduced before about the percentages. It's around 14,000 seconds that you should consider at most. And then finally, you can also ask, I said furniture. You can also ask, what about doors, windows, and so forth? But if things become very small, simply neglect them. They might not be important in contributing to heat capacity for the room. Finally, I have with me an Excel sheet that shows an example of application of this. I'll not go into the example. It will be uploaded on DTU Inside on CampusNet, so you can check yourself the formulas. But the example is about a room, which I have over here, 4 by 5 meters in floor area, 2.8 meters high. And then we have some walls in that room. Or indeed, I have one type of wall, which I have both as walls surrounding the room and also as floor and ceiling to the room. So it's a 2-layer wall I am considering for this here. And then what I have here on the slide is actually 2 variations of the same calculation. So one is that we have insulation on one side of the wall and that we have concrete as the other material in the wall. And my case 2, which is still in the same slide as I'll show you when I shift next, it's a similar wall, same materials, same thicknesses, only the order of the materials I have shifted. So which material faces first the room is different between using either of these 2 walls. So this I'm now calculating, or have done it, as it happens over here in the spreadsheet. I'll just point to a few of the things, although I don't show you the formulas, I'll just point to show you what are the values that we have. And no matter if we have concrete or mineral wool, 10 centimeters of both coming first, the U value of the wall will always be the same. So the 2 different walls, same U value. We have the same surface areas. Here you see some of the geometry that I've introduced on my drawing over on the whiteboard. And then we have contributions to the coupling coefficient, the heat transmission coefficient, if you will, from conduction through the walls and for ventilation, as I also spoke about in the previous slide. And the total coupling coefficient for the whole room is the sum of the contributions from conduction and from ventilation. So that's what we calculate here in the spreadsheet, and we get the same numbers no matter which of the two materials comes first. On the next slide, I have up here, I need that some heat gain, so two people are coming in, so we have suddenly 300 watts extra in the room. Inside temperature is initially 20 degrees, like also the outside temperature, so that's something we need just to have something to calculate. But I need to calculate the heat capacity, and that is seen from the room going into the materials. So either if concrete is facing the room has a high heat capacity, well, that's a number that's calculated, and if it's mineral wool that faces the room, it's a much lower value. So that's what makes the difference between the two things. Sorry, I'm slowing you here already the result, but that is what comes from calculating with our formula. Here it's calculated hour by hour what will be the inside temperature in the room. And what is the case is that when we have concrete facing the room, so much heat capacity is in the room that the temperature increase is very slow. So there's not much temperature increase during the 8 hours that the two people are coming to work in the room. Opposite, if it's the insulation that faces the interior, the room, well, then there's very little heat capacity. So for the same gains, the same geometry, the same everything, heat loss coefficient, but now the temperature increase is so much faster. And that's the whole point. Now you're able to calculate such things with this simple, relatively simple, Bowe-Adamsson method. So thank you for listening in to this. I hope you enjoyed it and can use it for the future. Thank you.